Last lecture we have seen that the term by term integration of a Fourier expansion leads to the correct result. That is, the left hand side and right hand side is the same, but this is not true for the differentiation. So we shall consider the term by term differentiation of Fourier expansion. As we have seen in the last class, that a function f of x satisfying Dirichlet's condition in a to b can be represented as this. Where we have used alpha is 2 pi by delta, where delta is equal to b minus a, and an we have written as a upon n to the power p, and bn has been written as b upon n to the power q, where p and q are greater than equal to 1. So per function which itself had discontinuity, for discontinuous function p is equal to q is equal to 1. So if we differentiate this term, then we find that a prime of x is equal to this term is 0, and then we will have, from this we will have a minus sign, if p and q are either p or q is 1, then if p is equal to 1, then n to the power 1 minus p is 1, and if we continue the series sum from 1 to infinity, n is equal to 1 to infinity, there is no term which causes the damping, so we will have an oscillatory term arising from sine function, and similar is for the second term. So the term by term differentiation of Fourier series is not, the convergence of term by term Fourier differentiation of Fourier series is not guaranteed. If we have p and q are greater than 1, then we can differentiate the series at least once. Say for the case, then ddx is not a valid operator, is not valid, or does not give you the correct result. If p is equal to q is equal to 2, then ddx can be executed, can be performed, but not d2x dx2, because If you differentiate it once, then the term will be n to the power 1 minus p is 1 upon n, and if we differentiate it twice, then it will be n minus p is equal to 1, and there is no term which causes the damping, so it is not possible to differentiate such series twice. And similarly extension can be carried out. If the series our argument is correct, then we cannot differentiate this, because if we differentiate this on the left hand side we will have 1, and if we differentiate on the right hand side, the result will not be a meaningful one. On the other hand, we can differentiate it once to get the correct result. From this logic, it seems that it can be differentiated because x cube function, but not because of the presence of 1 by n term, that is to say the function itself has a discontinuity. So the Fourier coefficients will have 1 by n dependence, and that will lead to the erroneous result. Let us see by differentiating these two one by one, and then we shall come to the a general theory which will show us what should be the condition that should be satisfied by the functions so that the differentiation yields the correct result. If we differentiate it, we will have d dx. Then on the left hand side we will have 1, and on the right hand side we will have 2c by pi, then x by c. So this is 2c by pi, and if we differentiate it we will get this term, and there will be a factor n pi by c cos of n pi x by c. This c cancels out, this n cancels out, pi cancels out, so we will have 2 summation over if we put x is equal to 0. Then the right hand side is which is not equal to the left hand side. This is not equal to the left hand side, as we have argued earlier. On the other hand, if we differentiate this function has no discontinuity, so we can differentiate this to get the correct result. So we will have on the left hand side 2x, on the right hand side this part is 0, then 4c square pi square minus 1 to the power n upon n square d dx of differentiation of cos will bring a negative sign, so this is 4c square by pi square n plus 1 by n square, then we will have n pi by c on simplification This gives this 1 pi cancels, 1 n cancels, 1 c cancels. So we will have 4c upon pi this is indeed this result. If we differentiate this, we will lead to a wrong result. If we differentiate the f3, we will find that we have landed up with a wrong result. Let us see what we get. So on the left hand side we will have 3x cube, 3x square. On the right hand side, this part is constant, 2c cube by pi then differentiation of this. Pi square and then n pi by c times cos of n pi x by c. Now this becomes c square, pi goes out, and then we will have 2c square or x by c. This is the first term, and from the second term we will have 12 c square by pi square this, if we consider with this term, or x square is equal to 2 by 3 c square minus 1 to the power n plus 1 cos n pi x upon c plus 4 c square pi square if we use this, it is x square minus this part is, if we write f2 expression of f2, this is x square minus c square by 3. So this is 2 by 3 c square plus x square minus c square by 3. For this part we have used f2, the expression for f2, and we have this term, so it is x square minus this. So we see that x square term cancels and c square cancelled, the 3 in the denominator gets cancelled. So we will have 2 times because if we write because if we put x is equal to 0, if x is equal to 0, we will have 2 times summation over minus 1 to the power n is equal to 1. This is not correct. And if we put x is equal to c, then we will have 2 into summation over 1. This is equal to 1. Again absurd. This is oscillatory. This is the left hand side is oscillatory, and for this the left hand side is divergent. So the conclusion that we have come here, that we cannot blindly differentiate a Fourier expansion. In Fourier expansion, we have a function on the left hand side which is a piecewise regular function, and right hand side we have a expansion. If we differentiate both the sides, then the differentiation of the right hand side term by term may not lead to the correct result. It will lead to the correct result only when the function that which we are differentiating doesn't have discontinuity. That is, the A and B dependence, the dependence of A and B, the Fourier coefficient must not involve 1 by n term, which is a signature of the discontinuity of the function itself. To see when the term by term Fourier expansion of a series will lead to the correct result, we are considering a general derivation here, and this derivation is done in the book of Tang, Katie Tang. Consider f of x which satisfies Dirichlet's condition. So we write which satisfies Dirichlet's condition, and a to b recall the definitions of definition. A0 is equal to 2 by delta f of x dx from a to b, an and similar definition for Bn. If possible, we expand a prime also in Fourier series. A prime. We assume that a prime also satisfies Dirichlet's condition, so we can write it a0 prime by 2. So let me first write, and then where a0 prime is 2 by delta a to b an prime is 2 by delta and bn prime this is one definition. Here we assume that f of x and a prime of x satisfy Dirichlet's condition. This is our assumption behind writing this. If we differentiate it directly, what happens? We get on the left hand side a prime of x, on the right hand side this part will be 0, differentiate, this is the differentiation of this part. This is the differentiation of the second part. This is this part. So, if the direct differentiation, term by term differentiation of a Fourier series expansion had to give the correct result, then these two expansions must match. Then we see what are the conditions to be satisfied for the function to, so that this differentiation, that is this result, will be at par with this. Now let us start with calculation of a0 prime. Let us start with the calculation of a0 prime. Now a0 prime is 2 by delta some integration from a to b f prime of x dx. This is the definition. This is 2 by delta f of b minus f of a. This is not in general related to a0, but if we consider this expansion, then it has to be 0. That means one condition is if a has to be a b. Now come to the an calculation. We consider this is as the first function. Then integrating by parts, there will be a minus sign and there will be a minus sign from the differentiation of this part. So we will have 2n pi by delta integration of f of x so the first term is this first term, a to b, and the second term, if we connect this, associate this with this is simply bn. This is bn, so we will have 2n pi by delta pn. Similarly, bn prime would be if we compare this term, this is basically, this part is basically bn prime and this part is basically an prime. But there is a, if we come from this definition, there are extra terms involved. So these two result, this result will match with it if we can set this part is equal to the this part, the part that is underlined by red color, if they are 0 together with this. So the term by term differentiation of a Fourier expansion will give correct result provided condition is f of a is equal to f of b. Second condition is that f of x cos of 2n pi x by delta at the limit ab is equal to 0, and so is for sine part. And most important that both fx and fx prime satisfy Dirichlet's condition. As these conditions are not in general satisfied by any function, so the differentiation, a term by term differentiation of Fourier series may not, or in general will not give you the correct result. And that we have seen in the three examples that we have considered. Only the f2 function leads to the correct result, while f1 and f3 leads to the wrong result.